Okay, lastly, let's talk about power. Again, a word that you may be familiar with, but you might not be able to define it very well because many people use it differently in regular life, sort of, so to speak. But power is the rate at which work is done. And when we talk about rate, we talk about how fast things are happening, right? So the concept here is similar to the concept of distance versus speed. If a cop pulled you over and said, "Do you know how fast you were going?" you wouldn't tell him 40 miles because your speed has two things going on. The distance you're covering is only one of those things. But the other thing that determines how fast you're going is the amount of time it takes you to cover that distance. And that's why speed is also a rate. It's a rate at which your position is changing. So that's why we use meters per second, distance divided by time. So a lot of times when we use the word rate, we just mean that we're dividing by something. And in physics, pretty much all the time, the rate is that we're dividing by time, the rate at which work is done. So again, remember in that people power lab that we talked about, the work that you did to walk up the stairs and run up the stairs was really the same, but it was the time that was different, right? So when we talk about power, it's not that we want to know the work that was done so much as how fast are we doing that work. Really important concept here for work. The equation for, not work, power. The equation for power is P equals W over T. P is our new variable, which is power. And the unit for power is, I'm going to write this out if I can right here, watts. W-A-T-T-S. I should have written that on the PowerPoint. Again, named after a person, but that's our new variable, capital W, which stands for watts. And you may have heard watts first time in your life. You may have heard the wattage on a light bulb. That's maybe the first time you've heard of the word watts. There are 60-watt bulbs, 75-watt bulbs. That tells us the power of the light bulb. It tells us how fast work is being done in that light bulb. And the work done there is electrical energy being changed into light energy. And how bright the bulb is determined by how fast that change is happening, the time that it takes to do it. W is work. We've already had that one. And T is time in seconds. Now I put this one here because remember, this is our old equation, W equals FD. Sometimes we could use this too, that since work is force times distance, we can sometimes substitute that one in there and we'll need to use it. Now let me give you a quick warning about what you're likely to do here. Notice at this point that we actually have two W's. Let's start over here. We have the W in the equation for work, right? We also have the W in the equation for power, right? So we have this W here, we have this W here. These two W's mean the same thing. These are both work, right? So the W in the equation, in any equation, stands for work. And remember, work is measured in joules. Right? So that's the W in the equation. But what would you think if you saw this? First of all, how do you say this? Well, this says 500 watts. So the W, this is not in an equation. This W that comes after a number, that's not a variable. All these are variables. These are letters that represent quantities. This letter does not represent the quantity. This is the unit, which is how we measure this quantity. And the unit here is watts. That W stands for watts, which is the unit for power, right? So these W's people get confused about. So here's the way to tell them apart. If the W is in the equation, that W stands for work. But if you're reading a problem and you see a number like this, the W that comes behind the number does not mean work. That W stands for watts, which is the unit for power. So two W's, which means different things. Be careful about getting them confused. So let's look at these two practice problems and we'll be done with power. A machine performs 500 joules of work over a period of 100 seconds. Calculate its power output. Again, with power, the amount of work done isn't so important as the amount of time it takes to do it. You ran up the stairs faster, and because you did the same work in a smaller amount of time, you had a greater power. So what does this problem give us? Many people say this. I hear these words come out of their mouth. What does this problem give us? Well, it gives you the joules. And it's sort of correct, but I want you to be able to tell me what variable that is. It doesn't give us the joules, because when you say it gives us the joules, quote unquote, you're likely to do something like this, right? But this isn't correct. J is not a variable for anything for us in this particular unit. It doesn't give us the joules, it gives us the work. It gives us work, right? So the work is measured in joules. It gives us 500 joules of work. What else does it give us? It doesn't give us the seconds, it gives us the time, right? T is time, and it's measured in seconds. So it gives us the work, gives us the time. It says calculate the power. P is power, and that's what we want to know. What's the equation that has all that stuff in it? Well, this one's super simple. Power equals work divided by time. We simply plug in the work. We plug in the time. 500 divided by 100 gives us 5 watts of power. That's 5, and the unit for power is watts. Pretty simple, straightforward problem. The next one is just a little bit more complicated, though. We have an electric motor that lifts an elevator 9 meters in 15 seconds by exerting an upward force of 12,000 newtons. What power does the motor produce? So let's just look at this question and diagram it. It gives us a distance or a height. Depends on what you're using there. It could be a distance, could be a height. I'm going to keep it distance for right now. Maybe we could put both. 15 seconds is time. And then it gives us an upward force of 12,000 newtons. Knowing the variables for all of these things is very, very important. Right? It doesn't give us the newtons, it gives us the force. It doesn't give us the seconds, it gives us the time. It doesn't give us the meters, it gives us the height or distance, depending on what it is. And it asks for power, and the variable for power is P. That's what we're looking for. So to write that down, givens, we know that, let's just call it distance for now, is 9 meters. We know that the time is 15 seconds. And we know that the force given is 12,000 newtons. Unknown, what they're asking us to find is power. So I'm going to write P over here for power. And now I got to find an equation that has all this stuff in it. And some people get confused because, well, I know the equation for power is W over T. Yes, that's true, but the problem here is we do not have the work. They don't give us work. So this is where we have to use the second part of the equation that you wrote down, which is FD over T. Remember, work equals force times distance. And we do have those two things here. Now remember, this might come into play as well. It doesn't here because they've already given us the force required to lift. But it could have said, it could have given us just the mass of the elevator and not the force. We would have had to do this to calculate the weight of the elevator first, and that weight would have gone in for our force up here. But the equation here is power equals force times distance divided by time. Computer, something's there. So now we can just simply plug in those numbers. Force was 12,000 newtons. The distance it gave us was 9. And the time is 15 seconds. This is simple multiplication and division. The order does not matter here. You can multiply these first. You can divide in any order, but ultimately, at the end of the day, it's these two multiplied, divided by 15, and you should get 7,200 watts. And that is how to calculate power.